So in the last video we looked at the magnetic field shapes around a single current carrying wire, a loop of wire and a solenoid. So in the single current carrying wire there you can see the current is going in the direction of the thumb, positive current I, and you've got the magnetic field is shown by the fingers wrapping around that wire, and it forms the concentric circles there in that plane of the page. So don't forget the circles get further apart because the field gets weaker. And there's an example of the right hand grip rule or curl rule there. Okay, so you can also do it for a loop of wire there which is carrying a current. So electric current's coming through the bottom here. So if you use your right hand rule in this area here, you will find that as the current goes up the page, it's going to go around the back of the loop and in through the centre of the loop, left to right. So you've got that field shape there. So don't forget that one. And don't forget for a solenoid one here, you've got a fairly uniform one through the middle as they're all adding together. And you've got them going out and separating it as they get to the ends of the poles and really weak on the sides here. And there is a formula, but again that formula is not in the course at the moment. Now what we're going to look at today here is what would happen if you put a wire carrying a current in an existing magnetic field. In this one here we've got a current carrying conductor going into the page here, so it should have a cross at the back which is not visible. Now that would mean that the field would wrap around there clockwise if you check it with the right hand rule. The thumb goes into the page, the fingers will wrap around clockwise here. Now if you add those fields together, the one that's an existing field with the one formed by the wire, you'll find that on this side here they're going to go in the same direction. You'll get quite a strong field there. On this side here they're in opposite directions. You'll find the field tends to cancel and be a lot weaker. Now the stronger field on the left here will push this wire off to the right and exert a force on the wire. So this results in a magnetic force caused by the current carrying wire being in an existing magnetic field. Okay. Now there's a right hand palm rule that shows you the direction of that force here at 90 degrees, and there's also a rule telling you the size of that force. Okay, so just bear that in mind there. So if you look at this, if you had a magnetic field going from right to left here, from the north to the south, that's the way our north test pole will go. B is the field strength there. It's going from right to left. So you've got a current going up the page here in a conductor. So you still use your thumb as the current going the direction there for intensity of current. You field now, instead of wrapping around the wire and showing you how the field is wrapping around the wire, we're more interested in the field that it's sitting in which case the field is going from right to left here. So you put your fingers in the direction of the field, okay, right to left. And the palm, the way the palm pushes, will actually show the direction of the force here. So this is called the right hand palm rule, and there's similar rules that show you the direction as well, but this is the one I've always used. So the right hand palm rule will show you the direction. So for example here, if you put your thumb in the direction of the current, the field into the page there, so stretch your fingers straight out into the page, you'll find that the force is going to be up the page. So we just sort of show you that. Current is going to your right, field is going into the board, it's going to lift up like that. So that force should be 90 degrees up the page here, using the right hand palm rule. If you look at this one here, the current will be going from right to left, so that's your thumb that way. Your fingers are going to be pointing downwards. You'll find that the force here is out of the page, 90 degrees out of the page. Look at this one here, the current's going down, so the thumb would be down. The fingers would be going out of the page because this field here is out because it's a series of dots coming towards you for the arrow. So if it's coming out of the page, you'll find the force is to your left with your palm if you tried that one. So just give that one a try. Now, some things to be aware of in terms of size of this field. So a couple of things to bear in mind is there are lots of proportionalities. The first proportionality is that the force will be proportional to the intensity of current. Because if you have a larger current going through the wire, you'll have a bigger field around the wire, bigger interaction, you get a bigger force. Okay. The size of the field itself that it's sitting in is obviously important. If you use stronger magnets when you do this, you're going to get more force as well. In fact, double the field strength, double the force. It's proportional. So same with the length of the wire. The more length of wire you have in that field, the bigger the overall force is going to be. Okay. And finally, you've got to consider the actual angle, because it turns out if the current is parallel to the field around here is actually this way, don't forget, and that's at 90 degrees to the existing field, so they're independent, they will not affect each other. The force in this case would be 0. Okay, so when the current is actually parallel to the field, you get 0 force. You get a maximum, it turns out, when the opposite occurs. Then when you go and do this at 90 degrees, if your current is straight up at 90 degrees to the field, where theta is 90, you will get your maximum force. Okay, so there's obviously a range in between there. So just remember, when the current is parallel to the field, you hear nothing. There's only a proportion of the wire with the current carrying in a 90 degrees direction to the field, which is going to give you the force. So we're actually trying to calculate this component here. So if you check it out, that's actually the sine of theta that gives you that component there of the current element. Okay, so we're going to use those there. Altogether, you've got this thing called F equals BIL sine theta, or F equals Bill sine theta if you like. And you'll find they put a triangle L there in most cases. So that's the size of the force, and use the right-hand palm rule to get the direction. Now in this demonstration here, we've got the north pole, the south pole, so the field is going up, that's the way the fingers will go. The current is going from left to right here, from positive to negative. So if the thumb's to the right and the fingers are going up, you'll find your palm is pushing out of the page here, or in other words, towards us. So you see the result of that will be this. Okay? So you get that strong force coming outwards. And this is used in speakers and so on. So let's just look at some examples here. If we're looking at trying to find the force on this current carrying conductor that's in that magnetic field, so let's find the force on the wire. We're just going to be using that Fred equals Bill, or F equals Bill formula, BIL sine theta. And in this case, we've got a magnetic field strength here of 2 × 10⁻³ Teslas. So that's what magnetic field strength is measured in, times by the intensity of the current, which is 0.5 amps. And we've got a length in the actual field here that's 40 centimeters, which should go as 0.40 meters. And we want to do the sine of the angle here that it makes with the field, and that's 60 degrees. So sine of 60. If you put that in, you'll get a force in newtons. And what we're interested in is which way will the direction go. So if your thumb is going up the page here for the current, field going left to right with your fingers extended, you find that your palm will push inwards. So it's 90 degrees into the board, into the page in this case. So if you do that, you get about 3.5 × 10⁻⁴ newtons. Okay. What we've got here is a wire experiencing a force of 0.3 newtons. So I told you the force this time of 0.3. And we're trying to find the field strength B. So this time the current is going to the right. We've been told the field, now the field's got crosses here, which means it's going into the board, by the way. So we've got a direction for field. So to find the field strength, first of all, we've got to find B, we've got F, we've got I. This is making 90 degrees with the field because the field is into the board. This is going parallel to the page, or in the plane of the page. So that's a 90-degree angle. So the sine of 90 here would be 1. So you're going to get maximum force here. So we need to rearrange F equals BIL sine theta. Forget the sine theta here, to get B equals F divided by IL. So the force here is 0.3 divided by a current of 3 times by a length of 0.2. Okay, so in that case the field strength would be 0.5, so you've got 5 × 10⁻⁻1 Teslas. Okay, for direction, if your current is to the right, would be your thumb. Field strength is into the board, that's where you put your fingers. Your palm would push upwards there, so the force is upwards here at 90 degrees up the page. Now let's just try and put some of this stuff together here. You remember with gravity you've got a formula for the force between any two masses, given by this here, Newton's law. The gravitational field is the field strength at a certain point, so by definition you put a test mass there. It's the amount of force acting on a test mass, so in newtons per kilogram. And you can also work out the field strength by just using the source of the field, the mass here, and how far away from it is. So we had those three before. And you can do similar things with electric there, of course, electric force between two charges. The electric field is the force on a test charge, a positive test charge. And you could also work out the electric field if you know the source of the field and how far away you're going. This same thing applies to magnetism. Where you've got Newton's law, Coulomb's law, there is a formula between any two wires carrying a current called Ampere's law. So that's actually the same sort of thing. The force would based on the two currents, the distance between them, and a constant, which is 2 × 10⁻⁷, but also the length is important. So there's a common length here between the two wires where they're actually parallel to each other, that length there, where they're overlapping, where their fields interact, that would be the length. This is not in the course though, but I'm showing you for, I guess, completeness. So that Ampere's law is very much in line with Newton's law and Coulomb's law. So similar to that then, if you wanted to define the magnetic field at a point around a wire, you would normally have to do some sort of a test mass, test charge. We need to put something there that would respond to the field. So the best thing to put there would be another wire there which produces its own magnetic field. So this is like a test wire, if you like, called a current element. So it's important you have the current of a certain amount there, say 1 amp, with a length of a meter there. So by definition then, the amount of magnetic field strength at this point here, similar to this idea, is the amount of force acting on a current element, a length of wire of 1 meter, carrying one current of 1 amp. So there you go, that would be the force on a current element, but the angle is important in that as well. So that's the sort of definition that's consistent with the rest of them here. And you could of course then do a formula further down here around any y, and you'll find it actually turns out to be a constant, same as the one over here, times by the current, times by, divided by the distance. And this time it's not an inverse square law because the field's not coming out in straight lines, so you don't get a quarter of the force when you go twice as far away. You only get a half. So when you go twice as far away here, the field would be only a half of it. 3 times as far away, be a third. But again, that formula is on the course. The one we are focusing on the course is this one here, because that one, if you rearrange that, you get this idea of F equals BIL, and the sine theta is important. So that's where it comes from. We're only focusing on that middle bit here in our Year 12 course at the moment. So if you look at Mr. McGarry's PowerPoint here, he's actually made that definition there. The magnetic field strength is defined as the force per unit current element placed at 90 degrees to the field. So that's the same sort of idea as a force on a test charge or the force on a test mass. So it's actually newtons per ammeter per meter, but that's called a Tesla. Okay, so the Earth's got a magnetic field strength in certain points of 50 microteslas. All right. And if you rearrange that, you get F equals BIL sine and BIL sine theta, obviously. Now in our next video, we're going to look at the applications for these forces of a wire in a magnetic field, and it's going to be the moving coil loudspeaker. We'll try that next. Thanks.